Welcome back to CS 520. In this session I want to talk about the memory hierarchy. What's the purpose of this hierarchy? Well, we want to create the illusion of a very large memory that can be accessed with high speed. It's an illusion because the high speed memory is expensive. So we want to try to make it look like we've got high speed memory, but we're actually using lower cost memory. Let's look at some technologies. So if I'm looking at using static RAM, I can improve my access time by a factor of 10. I can lower it by a factor of 10, but it comes at the cost of a factor of 100. Okay. And similarly, if I can back up my memory with disk, use disk for memory that's not being used very often, I can greatly reduce the cost, but it comes at a great increase in the access time. So what I'd like to do is keep things in high-speed memory when I'm using them and back off, place things in lower speed memory, even all the way back to disk if it's a piece of data or program that I'm not using very often. Again, these are just sort of ballpark figures to give you an idea what's going on. But the approach is to try to leverage this very high performance but high cost memory as best we can by putting things in it that we use frequently, and stuff that we're not using frequently we'll back off to lower levels in the hierarchy where it doesn't matter what it costs to actually access it. So you might be thinking, how can this possibly work? How can we make this illusion work? Well, it turns out that programs exhibit something called locality. In other words, they access a relatively small portion of their address space in any small interval of time. So we talk about random access memory, but in fact programs don't fully use the power of that random access memory. They don't jump around accessing memory willy-nilly. There's usually some pattern that we can leverage to provide this illusion of having lots of high-speed memory when we really don't. And there's two kinds of this locality that we can talk about. One is called temporal locality, which means if a memory location is referenced, it will tend to be referenced again soon. So if we use something, we're likely to use it again in a short amount of time. So if we expect that to happen, we can put the item in the high-speed memory, and when it comes time to use it again, it'll be there. Okay. The converse of that is if we notice we haven't used something for a long time, then we can back off and move it lower in the hierarchy to lower performance memory, even to disk, because we don't expect to be using it again soon if we haven't used it for a while. So that's temporal locality. The alternative, the different flavor of locality, is spatial locality, which means if a location is referenced, locations whose addresses are close by will tend to be referenced soon. Okay, so if I touch the first element of an array, it's likely that I'm going to touch the second element of the array. So things near together tend to be touched together, accessed together. So let's just take a look at a little piece of code here and think about it in terms of locality. So just a for loop where I'm running over an array and summing up the contents of that array. So the access, the access to the variable I, right? These accesses to I are going to demonstrate temporal locality, right? I use I to do this initial test. I'm sorry, this initial assignment, then I'll do it for the loop bounds test. I'll do it every iteration. I'll increment it, and I'm also using it as an array index every iteration. So I is going to be used frequently. Similarly, sum is repeatedly accessed. So again, it's exhibiting temporal locality. But when we stop and think about the array, right, the array is going to be spatial locality, right? I'm just cycling through, iterating through, touching every element of an array. So I touch the first one, the second one, and the third one. So that's demonstrating spatial locality. So the basic principle here is we're going to place locations in a hierarchy in which least frequently accessed locations are lowest in the hierarchy. In other words, in lower performance but lower cost memory. And most frequently accessed locations are highest in the hierarchy, in the highest performing but also highest cost memory. So here's a picture. Right, we have a hierarchy where in fact the fastest access and also most expensive is putting data in registers that are inside the CPU. If we can keep our most frequently used values in those registers, then we're going to get really great performance. The next level down is memory cache. So with high performance memory, we'll try to keep the items that we're using frequently. Third in the hierarchy then is conventional memory, where the cost is sort of moderate and the performance is moderate. And finally, things that are not being used very often at all, we can back up on disk, which has very low cost but very, very poor performance. Okay. Now that diagram, by the way, I should flip back to that diagram. It's not drawn to scale really, right? I've drawn everything as an equal box. But in fact, the reality is you can probably better think of it as a pyramid, right? Where I've got, very small amount of data items I can put in registers. I've got a relatively small amount that I can have for cache. I've got maybe a bigger amount for memory, and then I've got a huge amount probably available to me for disk. Okay, so it's maybe better viewed as a pyramid. Okay. One other thing we can discuss with regard to spatial locality is that it's going to cause the systems to treat blocks of contiguous memory locations as a single unit. Because, for instance, in an array, if we access the first item, we're likely to access the second item. When I go to fetch something out of a lower performance memory, if I'm bothering to fetch one piece, I'll probably go ahead and grab a whole chunk of adjacent elements. So reading an array, and I won't just read the first item in the array, but I may read the first 4 or the first 8 or the first 16. If I'm bothering to go down and pay the cost of a slow memory access, I might as well amortize that over as much data as I can. So I'll go and grab a block. And again, this is relying upon spatial locality. I wouldn't do it if programs didn't exhibit spatial locality. If programs had true random access, there'd be no point in accessing the second element of the array just because I accessed the first. You might also think of this sort of treating things as blocks as a form of prefetching, right? The programmer requests the first element of the array, and I prefetch the second, third, and fourth because I expect the program to exhibit spatial locality. A couple of terms that we'll be talking about as we go through this is we'll talk about the hit rate. Here it just means the fraction of access is satisfied at an upper level. So we'll talk about the hit rate in cache, saying how often do we find what we're looking for in cache. Those are hits. How often do we not find them in the cache? do we have to go to normal memory to request them, as those are called misses. And we'll talk about the hit rate as the fraction of accesses satisfied at the upper level. So that'd be one important characteristic of a program. A characteristic of the system that we need to think about is the miss penalty. If I in fact miss at a higher level, what does it cost me in order, what time does it cost me to satisfy that access by having to go to the lower level to retrieve it? Okay. So how, in some sense, you can think of the miss penalty as how important is it for me to have a high hit ratio, because when I miss, I've got to go pay a big penalty to use the slower performing memory at a lower level. If we go back to the diagram for a minute, and just to give an extreme example, the disk access time is extremely slow relative to memory. Because the disk, for instance, has mechanical components so it's not just electronics, but we actually have to wait for heads to spin under for the platters to spin under the head to the right sector. So it's very, very slow. So we'll have a huge miss penalty when we don't find something in memory. We have to go to the disk. Okay. And similarly, there'll be a penalty to pay when we don't hit something in the cache. And we have to go to memory. There'll be a penalty there. Okay. All right. So, what are the key problems then in this hierarchy? Well, once you decide you're going to establish a hierarchy, the two key problems are when you're looking for a memory location, then you have to determine where the heck it is in the hierarchy. Right? It's not just in memory. It could be in the memory cache, or it could be in fact backed up on disk. By the way, the management of the registers is usually done by the software. I'm not going to talk too much about that in this class, but keeping data values in registers is either the decision of the programmer if they're programming at the assembly language level, or it's the decisions of the compiler, which decides to map certain variables from the user's program directly onto registers. So I'm not going to talk in this course too much that. It's really a topic for a compiler course. What we're going to talk about is how do you operate between the cache and the memory and the disk. Okay, so one of the key problems is, you're looking for a memory location. You don't just look for it in memory now. You have to say, is it in the cache, or might it be even on the disk? The second key problem is you have to make decisions about when to move locations up and down in the hierarchy. Again, I said early on, the general strategy is you want to keep things that are being frequently used up high, right? So if something's being frequently used, you want it in the cache. But if something is very infrequently used, we might as well put it back on disk because we're not using it anyways. Okay, so we have to make those decisions though. We have to move things around. And we have to think about it in terms of a pyramid too, because that emphasizes that we can't keep everything in cache, right? Memory is going to be much bigger than the cache. So there's going to come a time when the cache is full and we have to make a decision about what to do because we need to bring in something else into the cache and we'll have to replace something that's there. So we have to make replacement decisions when we move something up, because when you move something up, typically you got to move something else down. And in fact, the same thing happens between memory and disk. We have a limited amount of actual memory, and maybe the programs are much, much bigger than that. So we're making decisions about what parts of the programs to keep on disk and what parts of the programs to keep on memory, and that's dynamic, right? The program, as the program runs, we move stuff back and forth as required. So those are the two key problems that we have to think about as we study this more carefully. And in the future lectures, I'm going to first talk about virtual memory, which is really dealing with the bottom two sections. By virtual memory, we mean that the memory that we present to the user is bigger typically than what's available in physical memory. And so again, there's an illusion here where we have this huge virtual memory that's partially stored on disk because physical memory is actually too small to contain all the program. So that's one thing we'll take a look at. And the second one, we'll take a look at how memory caches work with a particular focus on how that impacts program performance. Okay, let's stop here.